Good morning, good evening, students. Rushti sir again to discuss some important topic for you. Let's take a break from all those electrostatics. Today I'm doing something on the thermodynamics plus fluid flow combined. Basically, this is a question from 2022 Jee Adv. And that question was a bit, to put it frankly, it was a bit confusing. And in my view, actually it is not in the syllabus. Okay? Let us say that question, let's look at the question. An ideal gas of density, she's saying ideal gas of density rho is equal to 0.2 kg per meter cube enters a chimney of height h at the rate of alpha, which is 0.8 kg per second. Perfect. From its lower end and escapes through the upper end as shown in the figure. Let us see the figure. This is the figure. It enters through the lower end. This area is A1 and enters through the upper end. This area is A2 and height is h. Right. The cross-section area of the lower end is A1 is smaller one, 0.1 meter square, and the upper end it is A2 is equal to 0.4 meter square, 4 times bigger, this upper end area. The pressure and the temperature of the gas at the lower end has been given 600 Pascal and 300 Kelvin respectively. But the temperature is given in the upper end as 150 K, only temperature given. The chimney is insulated, thermally insulated, so that the gas undergoes an adiabatic expansion inside the chimney. You can see this is a small volume to bigger volume. So expansion is taking place. Okay. And the adiabatic constant of the gas is gamma, which is gamma is equal to 2. Actually, this is a concern for me. He's saying ignore the atmosphere pressure. Okay, fine. But this gamma is 2 is a concern. Fine. So what are the questions? He has given options. It may be more than one correct option, but I've changed the question that he's saying all these options were based on these 4 questions. Find the pressure of the gas at the upper end of the chimney. Find the velocity of the gas at the lower end of the chimney. Find the height of the chimney. Find the density of the gas at the upper end of the chimney. Okay. So the solution, before a solution, I want to raise a bit some caveats here. You say, denote the value of gamma, it is given as 2. As you know, gamma for an ideal gas is 1 plus 2 by number of degrees of freedom. F is the 2 by F means F is number of degrees of freedom. If I put 2 here, gamma as per the question, then I am getting F as 2. Getting a degree of freedom for a gas as 2, ideal gas, looks very odd to me, because the smallest degree of freedom of ideal gas is 3, a monoatomic gas. Even if we ignore all the rotation, vibration, whatsoever, but translation will be will give it 3-dimensional, that will give a 3 independent modes of motion. Okay. For the argument's sake, we may say to make the calculation for the calculations involved in the question easier, he might have given this, or maybe there is some way we are ensuring that it doesn't have a one-dimensional motion is we are preventing, like maybe a 2-dimensional space. Okay, but that is doesn't look very comfortable to me given the physical situation here. Okay, fine. This number 2 is also note that the compressible flow is a compressible flow process. We have discussed in the flow process in fluids, it should be incompressible flow, and after that we have applied Bernoulli's theorem to that. So it's a compressible flow, and compressible flow processes are not under the scope of JEE, to be very frank. Now let us go for the solution. After raising the caveat, we'll go for the solution. See, this has been asked in the exam. Okay, these are the data given. A 2.4 meter square, T2, this 2 is top. 2 is top, so T2 is 150 Kelvin, as you know, is given in the question. Here the density of gas entering is 0.2 kg per meter cube. A1 area is 0.1 meter square, P1 600 PA Pascal, T1 is 300 Kelvin. As using adiabatic process. Adiabatic process, some basically expressions between T and V. T1 V1 to the power gamma minus 1 will be T2 V2 to the power gamma minus 1. Gamma minus 1 will be 1, 2 minus 1, 1. Okay. Okay, they're very simple. So for unit mass of the gas, volume per unit mass is 1 by rho. You see, this V1 is proportional to 1 by rho. Per unit mass, this is V1 is 1 by rho. Because M by V1 is rho, so V by M will be 1 by rho. So 1 by rho 1. So that means I can write is T by rho 1 to the power gamma minus 1 is equal to T2 by rho to the power gamma minus 1. So then rho 1 given 0.2, gamma minus 1 is 1 for both sides, 2 minus 1, 1. This is also this is T2 is 150 by rho to the power 2 minus 1. So that makes it 300 by 0.2 is 150 by rho 2. So rho 2 is 0.1 kg per meter. So the fourth question answer. Now let us go to similarly adiabatic in PV term, let us write. So V1 similarly can write as 1 by rho 1. So P1 by rho 1 to the power gamma will be P2 by rho to the power gamma. So from this very simply I can get P2 because rho 2 already I calculated 0.1. That value I will be using here. So that is P2 will be rho 2 by rho 1 to the power gamma into P1. P2 already just now calculated 0.1. P rho 1 given the question 0.2 whole square, that is 1 by 4. So 600 by 4 will be 150 Pascal. This is the question number 1. Very simple. I think this is just from the basic formula. Since the mass flow rate is same in both lower and upper end, obviously mass flow rate is rho 1 A1 V1 and it is rho 2 A2 V2. Rho is the density, area A is the normal area cross section and V1 is the flow velocity. So that is equal to mass flow rate. That is alpha given in the question. Alpha is, I think, whatever given it is. Alpha, I think alpha value given as if I remember clearly, it's 0.8 kg per second. Okay. Oh, fine. Okay. So V1 is how much then? Alpha by rho 1 A1. So 0.8 kg per second by 0.2 is rho 1. A1 is 0.1 given in the question, both of them. So 40 meter per second. This is the answer to question number 2. Similarly, V2 if you want to find out. So rho 1 by rho 2 from here. Rho 1 by rho 2. A1 by A2 into V1. So 0.2 by 0.1. 0.1 by 0.4. A2 is given. A1 is given. Rho 1 and rho 2 I have calculated 0.1. So 2 by 4, 1 by, so 20 meter per second. Okay. So they have not asked this V2 explicitly in the question. I may need that data later. Now only one answer remaining. That is to find the height. Okay. To find the height. In a flow process here, in a flow process where the density changes in this with the flow is the flow process where density changes with the flow, we call it compressible flow. The work done per unit mass by the pressure forces is given by volume per unit mass. That's our rating per unit mass. Now volume per unit mass into dP. This is flow work. Flow work is volume per unit mass into dP per unit mass. That is the work done. This is flow work done per unit mass by the pressure acting on the element. So this is 1 by volume per unit mass is 1 by rho dp. dp is minus dp. Why minus dp? I'm coming to the diagram here. This is one element. Flow is taking place like this. So take an element here, elemental volume. So mass is entering, mass is leaving. So let's say this side pressure is P plus dP, this side pressure is P. So what is the work done by the pressure force? P minus P plus dP into d volume. Okay, so d volume of this a very, very thin element, as thin as possible. So by that is dm by rho. So what is the flow work done per unit mass then? dWp. This is the dWp. Flow work done. This dWp per unit mass is 1 by rho into minus dP. I'm just explaining why it is minus dP. So dWp by dm, the flow work per unit mass from this is equal to minus dP by rho. That's what I wrote here. Okay, that's what I wrote here. You can say that I wrote here this. Fine. So this is dWp per unit mass. This minus sign because this is work done by the pressure on both sides of the element. Okay, this is the pressure work done on that elemental fluid per unit mass. So how to calculate that dP by rho? If the rho is constant, it's simple. I can take it out. dP minus P1 to P2 is it will be P1 minus P2 in by rho if rho is constant. That is just we calculate in the Bernoulli's theorem. If you remember, rho constant, you can take outside minus dB 1 to 2. That will be P1 minus P2. So it will be the work done by pressure force per unit mass will be P1 minus P2 by rho, which we have done in Bernoulli's theorem derivation. But here rho is varying. So what the flow work done here? That is dP by rho per unit mass. Total work done by pressure force will be integration of minus dP by rho. So fine. So P by rho to the power gamma is constant. That is P1 by gamma rho 1 to the power gamma 600 by 0.2 whole square because gamma is 2. So is it 15,000 SI units. So what is the that C is how much then? 15,000 SI units. So dP is equal to how much? D of C rho to the power gamma. So C gamma rho to the power gamma minus 1 d rho. So dP by rho will be how much? Divided by rho C gamma rho to the power gamma minus 1 by rho means gamma minus 2 into d rho. Okay, fine. Now integrate this dP by rho with a minus sign from rho 1 to rho 2. This minus C gamma rho to the power gamma minus 2 into rho 1 to rho 2. So that will be minus C gamma rho to the power gamma minus 1 by gamma minus 1 rho 1 to rho 2. So now you see minus C gamma rho to the power gamma minus 2 minus 1 minus rho 1 to the power 2 minus 1. So minus 15,000 into 2 by, because C is 15,000 I have found out, divided by gamma is 2 is minus 1 into 0.1 minus 0.2. So here it is minus 0.1 minus 0.2 is minus 0.1. So minus plus. So that becomes, so 15,000 into 2 into 0.1. So 3,000 plus, because here this is the minus, this is minus. So this is the pressure flow work done. That is delta W pressure per unit mass on the fluid. On the fluid. This is by the pressure on the fluid. So work done by the gravity force, then how much beta? By the gravity means it is negative of the delta U gravity per unit mass. That is minus of M is 1. So G H2 minus H1. So G into H1 minus H2. H1 is the base level, that is taking a 0. And this is H2 is H. So it is G is 10. 0 minus H. So minus 10H. Clear? So two work done I calculated. One by pressure force, that is the flow work. And this is the gravity force work done. Then per unit, all are unit mass. So gain in kinetic energy per unit mass how much? V2 square minus V1 square. Because M is 1. by 2, V2 square by 2 minus V1 square by 2, 20 square by 2 minus 40 square by 2 minus 600 joules per kg. So these are the 1, 2, 3. These are the work done by 1, 2 are work done by forces. One is by pressure. There's a flow work by pressure, and this is the gravity work. This is plus 3000, is minus 10H. So if I sum of these two work done per unit mass, I will get the gain in kinetic energy per unit mass from work energy theorem. So assuming a steady flow, applying the energy balance along a streamline. Steady flow means a streamline flow. So delta W pressure plus delta W gravity should be delta K. So delta W pressure, how much we got? 3000. Yes, this is gravity force work done, how much? Minus 10H. So 3000 joule per kg minus 10H joule per kg is equal to what is gain in kinetic energy? Minus 600. Just I calculated V2 square by 2 minus V1 square by 2. M is 1 unit. So minus this 20 square by 2 minus 40 square by 2. 400 is 1600, 1200 by 2, 600 with a minus. So 3000 minus 10H is minus 600. So joules per kg cancel. So just H will be 3600 by 10. So 360 milliliters. Answer to question number 3. That's it. Okay. So this is a typical thing. We said other methods to do this also, but this seems to be this flow work concept is the most key here. Under the adiabatic condition, the flow arc which I calculated, that is in a continuous, in a steady flow equation, because this is two types of work we discussed, flow arc, non-flow arc. This is flow taking place, so flow arc has to be VDP, not PDB. Understood this? That you have to keep in mind. So that's what VDP were used, and by the pressure from outside work done will be minus of VDP. Pressure by the element doing work on the outside, it will be plus VDP. That means if there is a pump inside the element, so that one will be flow work will be plus VDP. But outside pressure, I have shown you very clearly in the diagram, P plus dP. If this side is P and in flow direction is increased by P to P plus dP, then the work done per second P minus P plus dP into d volume. D volume is dm by rho. Rho is the element density of this element, which will be changing from element to element. So then this is the dW. So dW by dm, dW by P means pressure. dW P by dm will be dWP per unit mass, that is minus dP by rho. Then that's what I integrated in the thing. Okay. So I am telling you for the important discussion. Let us go to the next page. So next page में जाके देखते हैं भाई हम लोग क्या डिस्कशन किया इस क्वेश्चन पे. जाएंगे सेकंड पेज में. ये लो आ गए हम सेकंड पेज में. फिर नोट में कुछ नोट दिया आपको. If the density rho remains constant, then what is minus, I just was discussing earlier, what is minus dP by rho? Work done by pressure force in the continuous flow motion. So that is minus 1 by rho. If rho is constant, rho is P2 minus P1, or P1 by rho minus P2 by rho. Gravity work done per unit mass as it is GH1 minus H2, because this is minus of delta U. Delta U is GH2 minus H1, minus of that GH1 minus H2. Gain in kinetic energy per unit mass is V2 square minus V1 square by 2. So you apply the work energy theorem, P1 minus P2 by rho plus GH1 minus H2 will be giving us the kinetic energy gain per unit mass. Okay. So applying work theorem, by getting P1 minus P2 by rho plus GH1 minus H2 is V2 square minus V1 square by 2. So this is nothing but a Bernoulli's theorem in an incompressible non-viscous flow, because rho is constant. So that is a very simple case. The next question I discussed, this is the What this is, this we call it, the whole thing which is given, we call steady flow energy equation. As per the first law of thermodynamics, for delta M mass flow, delta Q is delta E plus delta W for any process, flow or non-flow, where the E represents all forms of energy stored in a system. For pure substance, delta E will be delta E kinetic, delta E gravitational, delta U, this is internal energy stored in the U is the molecular structure. So delta E will be E2 kinetic minus E1 kinetic plus E2 gravitational minus E1 gravitational plus U2 minus E1. That is equation 2. So delta W is it can be a flow process or like VDP work plus external work. External work is what? Suppose this gas is going and rotating a shaft or something. We call that external work. In this question is not there, so we'll not bother about it. So delta flow is displacement work done by fluid on the mass dm at the inlet. Now it is by the fluid. The previous word is this on the fluid. So it will be P2 dV minus P1 dV. Okay. Delta extra shaft work, it is not there, absent in the question, so we are not bothering about it. So delta W will be this much only, that is flow work minus P1 dQ. dQ is the volume flow rate. That volume flowing, better let me write this symbol as, it's a clearly, this is, let me put it as Q beta. This is the Q. That's what. Substitute equation 4 in equation 1, we are getting delta M by Q. Equation 3, equation 4, equation 3. So thus delta W I'm substituting. So I'm getting this one. Delta Q delta M, delta V1 square by 2 GY1. Y1 is height. U1 by delta M, that is minus P1 dQ by M plus P2 dQ2 by delta M, V2 square by 2 GY2 U2 by delta M per unit mass. So then this one is, then I rewrite U1 square by GY, U1 is equal to this U1, capital U1 delta M is small U1, this per unit mass. All these things are now per unit mass. Okay. So now what is the U1? Just let us see here. I am writing very clearly also for you. Internal energy per unit mass, internal energy per unit mass. This is the volume per unit mass, specific volume, we call that V1 or 1 by rho, that is volume per unit mass, that is specific volume per, that is volume per unit mass, we call it by specific volume or 1 by rho. Okay. So delta Q by delta M, V1 square by 2 plus GY1 plus this is P1 V1 I bring to this side. So it U1 plus P1 V1. This is V2 square by 2 GY2 plus U2 plus P2 V2. This U1 U plus VV ko we give a name enthalpy. And these things are, all these are unit mass, then this is nothing but enthalpy per unit mass. This is a state function like your internal energy per unit mass. Internal energy is CVT. H will be CPT. That you will study later. From here also you can find out is CPT only. The specific heat at constant pressure into T will be the H value, or delta T will be delta H value. CV delta T will be delta U. This part you know, this you might not be knowing. So delta Q by delta M plus V1 square plus GY1 plus H1 is V2 square by 2 plus GY2 plus this is H2. Right? So we are writing H2 minus H1, then transport this side, is equal to delta Q by delta M को मैंने 0 लिया क्यों? Adiabatic process. These are all per unit mass. So H2 will be Cp T2 minus T1, V2 square minus V2, V1 square by 2 plus G, H2 is H, Y2 is H, Y1 is 0. So this. But Cp is gamma R by gamma minus 1. T2 I can write P2 V2 by R minus P1 V1 by R. So this is this. Okay. These are volume per unit mass. This here is also unit mass. So to get unit mass, I wrote volume per, this V2 is volume per unit mass. So RR cancels here. So gamma, this we got, RR cancels, we wrote this. Then gamma by this is V2 is 1 by rho 2, V1 is because volume per unit mass, so that is 1 by density. This is V1 also volume per unit mass, that is 1 by density. So P2 by rho 2, P1 by rho 1, gamma by gamma minus 1. This part is this. Okay, so this put the value now 2 by 2 minus 1, 150 by this P2 is 150, this is rho 2 is 0.1, this is 600, rho 2 is 0.2, 20 square minus 40 square by 2 plus 10 into h is equal to 0. Put the numerical values. So this becomes 10h becomes 3600, so h becomes 360 meter. So this is the steady flow energy equation application. You can skip it. Don't worry that I'm teaching you something which is not required. Just because the question was raised, I wanted to raise this. So like in many books, they will be giving something which you can skip also. So in my lecture, this is a point which I made, this one, which you can skip. This point number 2. Point number 2 you can skip. But point number 1 is that it's we can discuss if rho is remaining constant, it can reduce to a Bernoulli's equation. That you remember. Okay, so rho is not constant, then Bernoulli's theorem P1 by rho and P2 by rho will not apply. It depends upon what type of thermodynamic process it is, since the density is changing. And compression, thermodynamic compression is taking. Okay, I think you have understood this. Go through my lecture at the page 1 very carefully. I think you will be understanding many things, and many doubts must have been covered up. Many doubts must have cleared up in this, not covered up, cleared up. Never cover it out, must clear it quickly and definitely without covering it up. Okay, so now this is my, these are my credentials. Go through this question. I have taken a break from my normal capacitance discussion, which I will be back again. Now don't worry. I'll meet you again very soon, maybe tomorrow, with a new topic of discussion. Enjoy. No pressure. Study without pressure. Person who studies without pressure is the winner. Very simple law. Okay, so this is confusing question. So-called confusing question is not confusing, but definitely it's beyond the syllabus of Jee. Thank you. We stop here. We'll meet again next.